Today, we'll be talking about the space elevator that scientists are envisioning. Does this space elevator work like the ones we see in our buildings, malls, and everywhere else? And what is the mechanism that it works on? Stay tuned to find out more. Humans have accomplished some incredible feats in the last century. It took us just 66 years after the Wright brothers created the first airplane in 1903 to send a man to the moon. Our technical and scientific skills are undeniably impressive. Still, perhaps it's time we looked at the difficulties that go beyond what we've already previously envisioned. Maybe it's time for a space elevator. We're talking about super high, super thin tethers transporting passengers, satellites, and other cargo to high Earth orbit in train-sized elevator cars. If it's as simple as locking the doors and pressing the zero gravity button, you'll be able to transport all of your space infrastructures without having to spend any money on fuel. There is enough solar energy available to power the entire system, especially near the peak. The concept of a cable running straight up into the skies defies logic. The Earth is rotating at a staggering 1,000 miles per hour. This means that a rope attached to the space station at the correct distance of 60,000 miles up and with its center in geostationary orbit would need to be far stronger than any cable in an elevator shaft. The dream of a reusable spaceship was realized on April 12, 1981. When the Space Shuttle Columbia launched from Kennedy Space Center in Florida on the first Space Shuttle mission. Konstantin Tsiolkovsky, the same guy who came up with the renowned rocket equation that helped carry rockets into space, initially proposed the idea of a space elevator in 1895. The Eiffel Tower was under construction at the same time, and Tsiolkovsky's space elevator idea served as inspiration. He pondered whether humanity might construct a tower tall enough that its top would extend into space, allowing us to reach the stars without launching rockets. The elevator fantasy is still just that, a dream half a century after it was initially conceived. The theory is correct, but it also informs us that a long rope would carry so much tension that it would require ultra-strong materials to construct. The Burj Khalifa in Dubai is now the world's tallest building, reaching 829.8 meters. A practical space elevator would have to be at least 35,786 kilometers tall to reach geostationary orbit around Earth, more than 43 times the actual Burj Khalifa. Geostationary orbit is the distance from the Earth's surface near the equator at which the time it takes for an object to complete one orbit is equal to the Earth's rotational period in one day. This implies that if you were in a geostationary orbit over a location on Earth, say Pontianak, Indonesia, squarely on the equator, you would never move relative to that point. As a result, if you glanced down, the city would always be immediately below you. And if you stayed in orbit, the city would never move relative to you. Consider the game of tetherball, in which a rope is linked at one end to a pole and the other to a ball to grasp the notion of the space elevator better. The string represents the carbon nanotube's composite ribbon, the bar represents the Earth, and the ball represents the counterweight. Consider placing the ball in a constant spin around the pole, fast enough to keep the rope taut. This is the space elevator's basic concept. The counterweight rotates around the Earth, maintaining the cable's straightness and allowing the mechanical lifters to ride up and down the ribbon. Remember that the minimum height we'd need to reach for a space elevator to work is 36,000 kilometers. The system's center of mass, on the other hand, would have to be at the geostationary orbit height. Any lower, and the system would become unstable. The ideal size of the space elevator would be roughly 100,000 kilometers. Imagine this. The distance we're talking about is almost a third of the distance between the Earth and the Moon. At that distance, most of the elevator would have to be built in space. Along with many massive spacecraft and hundreds of people laboring in zero gravity to construct the elevator. Another option is to send a large spool of ribbon into geostationary orbit and then drop it towards the ground. At the same time, another spool is released upward to counterbalance the pull and keep the spacecraft in orbit. The initial vessel would be stationed in geostationary orbit with extensive cables stretching in both directions. This notion seems like something out of a science fiction novel, and it probably is. The engineering and material technology necessary for such a project is beyond our current capabilities. To fight the gravity that would draw this massive 100,000 kilometer structure down, as well as the centrifugal force and inertia of the counterweight, a space elevator requires extraordinarily high tensile strength. It must stay stable and functioning under high heat and cold, as well as unexpected atmospheric forces and radiation from space. On top of that, it would have to withstand regular bombardment from micrometeorites and solar wind particles. Is there such a thing as a substance that can meet all of these criteria? Carbon nanotubes, we believe, may be the answer. Carbon nanotubes are nano-engineered cylindrical carbon structures that are difficult to make and do not occur naturally. They are the stiffest and most robust material found to date, with extremely high tensile strength, which is precisely what we need for a space elevator. We wouldn't have to run any more cables to power the climber or elevator because they're electrically conductive. Even with its incredible strength, a carbon nanotube cable can only hold roughly 5,000 to 7,000 kilometers worth of its own weight before breaking, significantly less than the 100,000 kilometers needed for a space elevator. Nonetheless, technological advancements may one day allow us to reach a point where we can make the right material. A counterweight will be required at the top of the space elevator. In other words, just as the elevator is linked to the ground at the bottom, the elevator would have to be connected to something very substantial. The taller the elevator, the lighter this counterweight must be in order to cancel off the additional mass that you're introducing to the cable itself. The counterweight is required to guarantee that the mass above and below the height of the geostationary orbit remains equal. Hence, the centrifugal force drawing the system aloft is equivalent to the gravity dragging it downward. The counterweight for a space elevator with a minimum height of 35,786 kilometers would have to be about 1/3 the size of the Moon. Capturing an asteroid and bringing it into orbit around the globe would be one method to achieve this, after which we might construct the elevator to it. If the elevator is more than 50,000 kilometers tall, the tip of it would be going so quickly around the globe that it would approach escape velocity, which is the speed at which you would need to leave Earth's orbit. Liking this video so far? We'd appreciate if you could drop a like on the video, and make sure to subscribe to Space Facts. So, now let's understand, why should we build a space elevator at all if it's so difficult? All of these issues appear to have minimal return. It seems that building a space elevator is nearly unfeasible due to physical, scientific, and budget constraints. Is it even necessary to begin with? We can already launch things into space, and people live on the International Space Station. The answer is the expense. Currently, it costs roughly $10,000 to put 1 pound of cargo into orbit around Earth. However, the cost of interplanetary travel would be far higher. The elevator might cost as little as $6 billion. The cost of sending the same cargo after building a space elevator would be roughly $90, a 99% cost decrease. Building a space elevator may take technology and people that we can't even imagine today. But remember that aviation was still a far-fetched fantasy for the human race 150 years ago. From that perspective, there is no knowing how close we are to constructing a 100,000 kilometer space elevator. So basically, to figure out how the entire concept of a space elevator works is no easy task. And to have it work so smoothly in a day and age of advanced rockets will require science to stretch its arms to the fullest. Do you think this elevator will be made in the future? Let us know in the comments below. Thanks for watching. We'll see you soon.